In this machine learning class, we will see the multiple linear regression from 4th unit supervised learning. So here we will see what is multiple linear regression. After that, the partial regression coefficient and best linear unbiased estimator, that is blue, or Gauss-Markov theorem. And the next one, the problems in multiple linear regression analysis. There are two problems. First one is multicollinearity and second one is heteroskedasticity. After that, we will see what is bias and variance in regression model. Then we move to improving accuracy by using three different approaches. First one is shrinkage approach, subset selection, and dimensionality reductions. So we will see all those things one by one in today's class. Multiple linear regression. So we know already that the regression is finding the relationship between two variables, that is the dependent variable y and independent variable x. Okay, so based on the x value, we need to find the y value. Okay, so y equal to f of x, which is equal to a plus bx. Here we know that b is a slope and a is x y intercept. Okay, so these are the things we have seen already in our previous class itself. Now let us come to multiple regression model. Okay, here the target variable y is the dependent variable and it is dependent on two or more independent variable. That is, the x value are more here. Okay, based on all these x value, we need to predict the y value. Okay, now the y value, that is the dependent variable, is continuous value. Okay, so the numerical continuous value normally. Now the equation for the relationship with two predictor variables, that is we are having two x values, x1 and x2. Okay, y cap means we need to predict the value of y, right? Y cap equal to a plus b1 x1 plus b2 x2. So this is the equation for the relationship with two predictor value for multiple linear regression. Okay, let us see what is a, b1 and b2. So in this equation, a is nothing but the intercept and b1 b2 are the partial regression coefficient. Okay, so the parameter a is the intercept of the plan. That means the regression line crosses the y-axis when x equal to 0. So that is called as a value, or it is otherwise called as y-intercept. Right? When come to b1, b2, these are partial regression coefficient. Okay. Now the parameter b1 represent the changes in mean response corresponding to unit change in x1, but x2 is constant. Okay, so b1 is directly related to x1 value and b2 is directly related to x2 value. Okay, when x1 is constant. Okay, so b1 b2 are partial regression coefficient. Next, let us see one example for this multiple linear regression current real estate problem. That is, we are going to buy one property, that is home. Okay, and the dependent variable here is price of the property, that is y equal to a rate of the property, for example. Right, now the rate is dependent on which are the parameters. Okay, so this is directly dependent on the area mainly, isn't it? So if the area is high, then the rate will also be high, right? So apart from this area, and other parameters are also very important, right? First one is location. If the home is in heart of the city, then definitely the rate will be very high. Okay, and floor, which floor the flat is located, and number of years since purchased, that is the age of this home, and etc. So based on all these things, the rate will be fixed for a particular home, isn't it? So the multiple regression equation shows that is the price of the property. okay, which is equal to f of area of property, location, floor, aging, and other amenities. Okay, so based on all these things, the price will be computed, right? So here the price is dependent variable and all the other parameters are independent variable. And this is the example for multiple linear regression model with two independent variables, that is two predictor variables. Okay, so in this diagram, this is y-axis, and this is x2, and this is x1. This is x1, right? So y cap, which is equal to a plus b1 x1 plus b2 x2. For example, y cap equal to 22 plus 0.3 x1 plus 1.2 x2, right? When n number of predictors are there, and then this is the equation, y cap equal to a plus b1 x1 plus b2 x2 plus b3 x3 etc. plus bn xn. Okay, now uh, for finding the best fit line, regression line, okay, we can fit either by a polynomial regression or curvilinear regression. Okay, we can use any of this. Polynomial regression means it may be a straight line. Curvilinear regression means it may be like this, positive curve or negative curve, whatever it may be. Next, let us see the best linear unbiased estimator blue, or Gauss-Markov theorem, or otherwise the assumptions in regression analysis. So totally we are having 8 assumptions. The first one is the dependent variable y can be calculated based on the linear function of specific set of independent variable x plus error term e. Okay, that means y, the dependent variable y equal to f of x plus e. F of x plus e. E is nothing but the error term, right? And the second one is number of observations n is greater than the number of parameters k to be estimated. Okay, for example, in a record we are having n number of parameters, 1, 2, etc. up to n parameters there. So among these n parameters, how many parameters we have taken for predicting the y value? Okay, so that is called as k. Here k should be less than n. So this is the second assumption. And third one is the relationship determined by the regression or only the relationship of association based on the data set. Okay, so the regression is determined based on the association based on the data set. How these parameters will be related to each other, right? And the fourth one is the regression line can be valid only over a limited range of data. Okay, if the line is extended, then that may lead to a wrong prediction. For example, so this is x and y parameter. Now our range limit is only these things. Okay, this data will be placed here. So the regression line is here. Suppose if we extend this regression line, this may lead to wrong prediction. Okay, that means the regression line is only limited to this area. The fifth one is if the business condition change and the business assumptions underlying the regression model are no longer valid. That is, suppose initially we have one business condition and the data are like this. Okay, so this is our regression model. Now the business condition changed, then this model is no longer valid. Okay, we cannot use the same rules for the new business, right? And the sixth one is the variance is same for all values of x. The variance is same for all values of x, then this is called as homoskedasticity. Okay, that is all y value is highly dependent on the x value. And the seventh one is error term. Okay, error term is normally normally distributed, and the mean of the error is expected 0. 0 means there is no error. Okay, so the errors are normally distributed and the expected value of error is 0. That means the 0 is no error. And next one, the error term are independent. So this is independent of both x and y value. Okay, that means there are no relationship between a particular x or y, or the error is never related to a specific value of x or y. Okay, so these are the 8 assumptions of the regression analysis. The main problems in multilinear regression analysis. So there are two main problems. First one is multicollinearity and second one is heteroskedasticity. Okay, multicollinearity means several independent variables are correlated to each other. That means independent variables are x1, x2, etc. up to xn, isn't it? So the x1, x2, that is the x values are normally independent, but here some of the x values are strongly correlated to each other. That means x2 value get changed, that will affect x3, x4, etc. Isn't it? So in this case, there is a very big problem in this regression analysis. And second one is heteroskedasticity. That means unequal scattering of data point. Unequal scattering of data point is called as heteroskedasticity. That means the observed values deviated from the predicted values ununiformly. Okay, so for example, this is the predicted data, but the actual computed data may be like this. There is no uniformly distribution, isn't it? So unequal scattering data is the heteroskedasticity, which is very big another problem of this linear regression analysis. The bias and variance in regression model. Here, the bias is similar to accuracy and variance is similar to prediction. Okay, accuracy we know very well. That is the difference between the original value and predicted value. That is actual value and predicted value, isn't it? So that is called as accuracy. And prediction, which refers to continuous estimation of the value. That is called as prediction. Okay, what will be the expected value is called as prediction. Now, the bias, high bias. High bias means low accuracy. Okay, bias means deviation. If the deviation is high, then accuracy will be very low, isn't it? So that is not close to the real value. That is the original value. Then high variance. High variance, which is equal to low prediction. Okay, if the variance is high, then prediction is low, that is values are scattered. Okay, that will not lies on the regression line, that may be scattered anywhere else. So this is called as variance. And low bias. Low bias means that is the deviation is very low. That means high accuracy. That is close to real value. That is close to predicted value. Okay, original value. Okay, the values are exactly lies on the regression line. And low variance. Low variance means high prediction. The prediction is very high. The values are close to each other. The predicted values are very much close to each other. Right? A regression model is highly accurate and highly predictive, then the overall error of our model will be low. Okay, that is, there is no error here. The model accurate will be very high, right? And a low bias means high accuracy, and low variance, that means high prediction, right? And this is highly preferable. Okay, that means error should not be there. and accuracy should be high and prediction should be high. Then only the regression model will be preferable. Suppose if variance increases, then the prediction will be low. That spread our data points increases. Okay, the spread of data points increases, less accurate prediction will be there. That means the data points will be spreaded all over. We cannot predict the regression. And next one is the bias increases. If the bias increases, then low accuracy, isn't it? So the error between our predicted value and observed value increased. Okay, original value may be different and predicted value may be different. Okay, so this is bias increases, that is low accuracy. Therefore, we need to balance the bias and accuracy, which is essential in a regression model. Improving accuracy of linear regression. Okay, here we can use three approaches. First one is shrinkage approach, and second one is subset selection, and third one is dimensionality reduction. Okay, first let us see this shrinkage approach. The first one is shrinkage approach, that is regularization approach. Here, limiting the estimated coefficient, that is shrinking the estimated coefficient. Okay, suppose if the coefficient are 10, we need to reduce that to 4, right? Then the variance will get reduced. That means the cost of negligible increase in the bias. That is, bias will get very much reduced if we shrink the number of coefficient, right? So this can improve the accuracy of our model. So if we want to increase the accuracy, then the number of coefficients should be very much limited. A few variables which are used in multiple regression models are not associated to each other. That means the y value is not associated with x1, x2, etc. Then those are called as irrelevant variables. If we use irrelevant variables, then unnecessary complexity will get increased. There are two best techniques there in shrinkage approach. First one is ridge regression and second one is lasso. That is least absolute shrinkage selector operator. The next one is subset selection. Subset selection means identifying a subset of predictor that is assumed to be the related to response. That means we need to select the best set of x values to predict the y value. Okay, so which are the x values will be very much suitable for predicting the y value. So that selection is called as subset selection. First, for this fit the model to OLS, that is ordinary least square algorithm, on the selected reduced subset of variables. Okay, for this there are two methods there. First one is best subset selection and second one is stepwise subset selection. When come to stepwise, there are two methods, that is forward stepwise selection and backward stepwise selection. Okay, that is 0 to k, k to 0. Okay. The first one is best subset selection. In this, fit a separate least square regression for each possible subset of k predictor. Okay, suppose if we are having k number of predictor, then we can select each possible subset and apply the algorithm. Then we can compute the accuracy of the predicted and original value. Right? So this is best subset selection. So here this procedure consider all possible 2 power k model containing the subset of p predictors. So to reduce the complexity of previous method, next we will move to stepwise subset selection. Okay, here this method will be applied into two possible methods. The first one is forward stepwise selection and second one is backward stepwise selection. The first one is forward stepwise selection. So this method starts with no predictor and each iteration one predictor is added. So for every iteration we need to test whether we reach the perfect subset selection or not. Okay, and finally, that is at the end of all iteration, we can easily identify which particular set of attributes will predict the exact y value. The second one is backward stepwise selection. This is opposite to our previous model, that is forward stepwise selection. Here, it starts with all k predictors, and every iteration it remove the least useful predictor one by one. Okay, it does not remove all the predictors randomly, but which is least useful predictor, that will be removed by every iteration. Okay, this is the third approach, that is dimensionality reduction, that is variable reduction. For example, now we need to predict y value by using the x value. Okay, we are having n number of x value, x1 to x2 etc. up to xn. Now if n is very high, then predicting the y value is very difficult. So what we have to do, we need to reduce the number of x values. Okay, for example, if it is only 3, then it is very easy to predict the y value. That means the number of variables is reduced using dimensionality reduction method. Variables here, x variables. Okay, and in dimensionality reduction, the predictor x are transformed and the model is set up using the transformed variable after dimensionality reduction. Right? So after dimensional reduction, we need to select only the best suitable independent variables, that is x variables, and the principal component analysis, that is PCA. PCA is one of the most important dimensionality reduction technique. Okay, by using this we can easily predict the best suitable x variables, which is used to predict the y variables, that is the target variable. So far we have seen the multiple linear regression from 4th unit supervised learning, and in this class we have seen the definition of multiple linear regression, partial regression coefficient, and the best linear unbiased estimator, that is blue, or Gauss-Markov theorem, or the assumptions of the linear regression model. After that, the problems in multilinear regression analysis, two problems there. First one is multicollinearity and heteroskedasticity. We have seen those two things, and the bias and variance in regression model, and this is very important to understand or improving the accuracy of linear regression. Okay, so three approaches there. First one is shrinkage approach, subset selection, and dimensionality reduction. Okay, in the next class we will see another important topic from 4th unit. Thank you.